In this video, we prove a result for truncated normal distributions that features in our proof of lemma 2 from the Heckman selection model. The lemma is as follows. Suppose that z is a standard normal random variable and c is some finite constant. Then the expectation of z, given that z is greater than c, is equal to little phi of c divided by 1 minus capital Phi of c. To understand where the term truncated normal comes from, notice that a normal restricted to be greater than c has basically had a chunk of it cut out or truncated away. So we are calculating the expectation of a random variable that is constructed by starting with a normal and cutting out a piece of it. The first thing we need is the CDF of this random variable. By the definition of conditional probability, the probability that z is less than or equal to some threshold t, given that it exceeds the constant c, is equal to the probability that z lies in the interval c to t, excluding c and including t, divided by the probability that z is greater than c. The probability in the numerator is 0 unless c is strictly smaller than t. So we start off after this equality with an indicator function that c is less than or equal to t. When that indicator function is turned on, so that t is larger to c, then the expression that we're going to calculate next makes sense and is well defined. So what is the probability of falling into that interval c to t, assuming that t is indeed bigger than c? Well, that's just the area under a standard normal to the left of t, namely phi of t, minus the area under a standard normal to the left of c, namely capital Phi of c. And similarly for the denominator, what is the probability that a standard normal exceeds c? Well, that's 1 minus the probability that it's less than or equal to c, which gives us 1 minus capital Phi of c. Using the CDF, we can now calculate the density of this truncated normal random variable simply by differentiating with respect to t. We obtain the following. As long as t is greater than c, we have little phi of t divided by the quantity 1 minus big phi of c. And when t is less than or equal to c, the result is 0. Now that we have the density of this truncated normal random variable, we can calculate its expectation. For a continuous random variable, we know that the expectation is equal to the integral from minus infinity to infinity of t times the density of that random variable evaluated at t, dt. Substituting our expression from the preceding slide, this integral becomes 1 over 1 minus capital Phi of c times the integral from c to infinity of t phi of t dt, where notice that we've cut out the range from minus infinity up to c because the density is 0 for that region. Now we will substitute the standard normal density function, phi of t. We'll pull the constant 1 over square root of 2 pi in front. That leaves us with the integral from c to infinity of t times e to the minus t squared over 2 dt. Now we'll evaluate this integral by substitution using the change of variables u equals minus t squared over 2, which implies that du is equal to minus t dt. So pulling a minus sign in front, we obtain the following, where we need to evaluate now from c to infinity, substituting back in for u rather than changing the limits of integration. When t is equal to infinity, we have e to the minus infinity, which is 0, so that term will vanish. And when we plug in a c, we obtain the following. Notice that the minus sign cancels out because we're evaluating the difference of minus e to the minus t squared over 2 at infinity minus the same thing evaluated at c. Now, inspecting the result that we've obtained, we have a factor of 1 over 1 minus capital Phi of c multiplied by e to the minus c squared over 2 divided by the square root of 2 pi. And that is precisely the standard normal density evaluated at c.